Hello there, and welcome back to the Sleepless Scientist. Tonight we'll wander into one of the deepest questions ever asked. How did the universe begin? If you find comfort in these journeys, feel free to like and subscribe, only if it feels right. Leave a comment with where you are and what time it is. I love seeing how far these moments travel across the quiet globe. Now dim the lights, let a soft hum fill the room, and let's begin. If your thoughts drift, that's fine. We'll still be here. The story of the universe's first second is not just a chapter in physics. It is a kind of cosmic lullaby, a tale written in particles and forces, in faint glows across the sky, and in numbers that seem too precise to be accidental. It begins not with firecrackers or fireworks, but with something stranger. The birth of everything we know from a place where words like before and after lose their usual meaning. To step into this story is to step into a time when time itself may not yet have existed, when space was not stretched out in any direction, and when what we call laws of nature had not yet taken their familiar form. You might picture the universe beginning with a bang, a sound echoing outward into a vast silence. But sound requires air, and space had none. There were no ears to hear, no emptiness to carry vibrations. What scientists call the Big Bang was not a conventional explosion. It was an expansion, space itself swelling from something unimaginably small to something vast enough to contain galaxies, stars, planets, and the quiet room you find yourself in tonight. The universe was not born into space. Space was born with it, unfolding like a sheet shaken out in the morning air, only faster, hotter, and with more consequences than any sheet of fabric could contain. It is hard to imagine a beginning that does not happen in anything, but happens as everything. Perhaps the closest comparison is the way dawn arrives. The light does not appear within the day. It is the beginning of the day, the sky itself changing its character, reshaping your sense of place. In the same way, the early universe did not erupt inside some larger container. It was the container coming into being, the framework of reality itself opening its eyes. We do not know all the details, and that is part of the wonder. Science often gives us not certainties, but maps of possibility, sketches of what might have been based on the traces left behind. Imagine walking on a beach long after a tide has passed. You do not see the water, but you see the shells, the ridges of sand, the pattern of seaweed. From those leftovers you infer the tide that once rushed in. The universe offers us its own ridges and shells, faint microwaves humming across the sky, the balance of hydrogen and helium in the stars, the way galaxies cluster as if drawn along invisible threads. These are fossils of creation, clues pointing back to the first second. Physicists give names to those earliest. Errors, Planck time, inflation, symmetry breaking. But for now you need not worry about the precision of those terms. What matters is the sense of scale. In less than a blink, in less than the flick of an eyelash, everything familiar and unfamiliar was set into motion. The universe was hotter than the core of any star, denser than any material we can create, more energetic than the most violent explosion. Yet it was also fragile, a slightly different balance in those first instants, and the cosmos could have collapsed back in on itself or stretched out too thin to ever form stars. It is tempting to think of this moment as chaotic, but in another sense it was simple. There were not yet atoms, not yet chemistry, not even light in the way we usually see it. Instead there were raw possibilities, fields and fluctuations, like an orchestra warming up before the first note. A violin string tightens, a flute breathes, a drum is tapped, but the music has not yet begun. In that first second, the universe was tuning itself, establishing the notes that would echo for billions of years. When you sit quietly and listen to your own breath, you may feel something similar, a rhythm older than thought, a beat continuing without your conscious effort. The early universe was breathing in its own way, expanding with each fraction of a second, cooling, shaping, preparing, If you had been there, though of course you could not, you would not have seen stars or galaxies or light. You would have sensed pressure, heat, movement, a density so complete that there was no place to stand apart from it. Some traditions and myths speak of beginnings in darkness, of worlds hatched from eggs or sung into being. Modern cosmology does not speak of gods or songs, yet it still finds poetry in equations. Mathematics tells us that space and time may have emerged from quantum froth, that every galaxy began as a tiny ripple, that every atom in your body carries a lineage that stretches back to those first instants. To ponder this is not to find every answer, but to feel the strangeness of existing at all. And so, tonight, as you drift into this story, let the edges blur. Imagine yourself close to that first moment, not as a scientist peering through instruments, but as a dreamer floating at the threshold of being. Around you there is no solid ground, only energy, vibration and possibility. A hush before the first word, a stage before the curtain rises. The cosmos is about to begin its play, and you have the rare privilege of sitting in the audience, eyes half closed, heart steady, ready to listen. What happened in that first second? We will walk through it together. We will step from the mysterious Planck era into the surge of inflation, from the splitting of forces to the gift of mass, from the vanishing of antimatter to the faint whisper of neutrinos. But for now we stand at the threshold, in the quiet before the dawn. The night is deep, the stage is set, and the universe is about to breathe its first breath. To ask how the universe began is to ask something stranger than when the sun will rise tomorrow, or when the next season will come. Those questions are about cycles, about patterns that repeat on a stage already built. But to ask about the beginning of the universe is to ask whether there was even a stage in the first place, whether time itself had a starting line, or whether the race has been running forever, without a true beginning or end. This is a question that has tugged at both philosophers and physicists, sometimes pulling them into the same conversations, sometimes leading them down different corridors of thought. For some, the simplest answer is that there was nothing before. The Big Bang is not just an explosion of matter into emptiness, but the origin of space and time themselves. Imagine a book. You can open it to the first page and there the story begins. You can turn back the cover, but there are no pages before the first. The book is not missing chapters, it simply begins where it begins. In this view, the Big Bang is page 1 of existence, and there is no page 0. The question of before becomes meaningless, like asking what lies north of the North Pole. The map ends not because of neglect, but because there is nothing beyond that boundary. Yet human imagination does not rest easily with boundaries. Many scientists have asked whether our universe might be only one bubble in a greater foam, a single balloon among countless balloons, each expanding into its own patch of space and time. This idea is known as eternal inflation, and though it sounds grandiose, it arises naturally from equations describing the rapid expansion that seems to have occurred in the first fraction of a second. If inflation can happen once, perhaps it can happen again, endlessly, with new universes budding off like seeds from a dandelion blown in the wind. Our universe would then be just one puff of fluff in a meadow without end. If eternal inflation feels too extravagant, there are other visions. Some cosmologists consider the possibility of a cyclic universe, a cosmos that expands, slows, and contracts, only to bounce back again in a new beginning. This big bounce suggests that the Big Bang we speak of was not the only one, but just the latest in a long sequence, each cycle erasing and rewriting the cosmic script. The imagery is almost musical, a heartbeat expanding and contracting, or a drum beat repeating across aeons. In this version, the universe is less like a book with a first page and more like a song on repeat, endlessly looping, familiar yet ever renewed. Another idea belongs to Roger Penrose, who envisioned something he called conformal cyclic cosmology. In his picture, universes rise and fall in succession, but not as bounces with clear endings and beginnings. Instead, the remote future of one universe, as all matter decays and only light remains, can be mathematically stretched into the birth of another. The end and the beginning blur into each other, scale loses meaning, and what we see as ashes of a dying cosmos become the spark of a new one. He even suggests that subtle rings in the cosmic microwave background could be echoes of those earlier universes, faint fingerprints of worlds before ours. String theory, with its imagery of vibrating filaments and higher dimensions, offers yet another origin story. In one vision, called the ekpyrotic universe, our Big Bang was the result of two immense brains, higher dimensional sheets colliding. To picture this, think of two vast curtains in a cosmic wind. They drift, they ripple, and eventually they brush against each other. The contact is not gentle but explosive, releasing energy that becomes a new universe. If true, then what we call the birth of everything is really the aftermath of a cosmic collision in a space larger than we can see. And then there is the most humble, and perhaps the most honest admission. We do not know. We may never know. Our telescopes can peer far, but they cannot see past the veil of the earliest light. Our equations can run backward, but at a certain point they collapse into infinities. The before remains wrapped in mist. Some scientists find this frustrating, others liberating. It means that imagination still has room to roam, that there are still horizons not yet pinned down. The unknown is not a failure but a companion, reminding us that even the most advanced theories rest on mystery. When you lie awake at night, listening to the hum of your surroundings, you might wonder how long the silence has stretched. How many moments existed before this one? The truth is that your life has a clear beginning, a first breath, a first cry. But the universe itself may not have such an obvious boundary. It might have a first moment like yours, or it might be more like the ocean, with waves rising and falling without a clear start. Each theory, Big Bang as first page, eternal inflation as endless meadow, Big Bounce as heartbeat, Penrose's geometry as ashes reborn, brain collisions as curtains clashing, offers a metaphor, a story, a frame. None is complete, but each gives a way to think gently about what it might mean for everything to have begun. As we move forward in this journey, we will leave behind the speculative landscapes and step into the terrain where physics is more confident, where the first second can be described not only with imagination but with numbers, with relics still visible in the sky. But before we do, it is worth pausing to honour this mystery. The universe may have had a first instant, or it may be part of something larger, older, stranger. Either way, you are here, listening, part of this story that reaches back beyond memory. The night outside your window is a small echo of the larger night, the one that gave birth to stars and galaxies, and eventually to you. To wander into the very earliest instant of the universe is to wander into a landscape where language begins to lose its grip. Our ordinary measures of size, heat, and time simply fail. We're used to talking about hot things like the surface of the sun, or dense things like the core of a star, but those are gentle candle flames compared to the furnace of the universe's birth. To take even a single step closer to the first moment, we need a new scale, a set of boundaries not chosen by human convenience, but carved out by the structure of physics itself. These are called the Planck scales, and they stand like tall gates across the road of knowledge. Beyond them, our equations wobble, our instruments cannot probe, and our imaginations must move carefully. Let us start with temperature. When you heat a kettle of water, it may reach 100 degrees Celsius before steam begins to rise. The surface of the sun glows at about 6,000 degrees. The centre of the sun is hotter still, 15 million degrees. When a star dies in a supernova, its collapsing core can reach billions of degrees, temperatures so extreme that atoms themselves are ripped apart, leaving only raw nuclei and electrons in a storm of energy. At the Large Hadron Collider near Geneva, protons are smashed together at energies that recreate temperatures of several trillion degrees, about 5.5 trillion to be more precise. It is a staggering number, hotter than anything in nature today, hotter than the centre of any star that shines. Yet compared to the beginning of the universe, even that is an ember in the fireplace, because the Planck temperature, the theoretical maximum meaningful temperature, is 10 million trillion degrees Kelvin. Written out, it is a 1 followed by 32 zeros. Numbers like this are so large that they begin to lose their meaning in speech. Instead, it is easier to imagine that if every other temperature we know, the kettle, the sun, the supernova, the collider, were stacked one atop the other like bricks, the Planck temperature would still tower above them, higher than any ladder could reach. At that height, even the concept of temperature starts to dissolve. Heat is the random motion of particles, but when energies are this extreme, the very idea of a particle is slippery. Now let us think about size. A human hair is perhaps 1/10 of a millimetre wide. A virus is smaller still, a few hundred nanometers across. The atoms that make up matter are measured in tenths of a nanometer. Inside those atoms, the nuclei are even smaller, about 1/millionth of a nanometer. Particle physicists talk of scales far tinier, measuring the reach of quarks and leptons at 10 to the minus 18 meters. Yet there is another gate, the Planck length, about 10 to the negative 35th power meters. It is a distance so small that if an atom were blown up to the size of the visible universe, the Planck length would still be a speck of dust, floating unseen in one corner. It is a scale so minuscule that geometry itself is thought to lose its clarity there. Space stops being smooth, stops being a fabric stretched evenly, and instead begins to foam, to bubble, to tremble with fluctuations. Physicist John Wheeler once called this picture quantum foam, a restless broth of tiny wormholes and micro-black holes appearing and vanishing faster than thought. Time, too, has its Planck limit. The Planck time is about 10 to the negative 43rd seconds. To grasp that, consider how quickly you can blink. A blink lasts about 1/3 of a second. Inside that span are quadrillions of Planck time stacked like grains of sand. If the entire age of the universe, almost 14 billion years, was squeezed into a single second, then the Planck time would still be a flicker within that instant, too quick to perceive, too brief to hold in the mind. It is the smallest slice of time for which physics has any meaning. Before that, our equations choke on infinities. Our predictions lose coherence. It is like trying to ask what sound a note makes before a string has been plucked. The music has not yet begun, and yet something is happening that will give rise to all music thereafter. These scales, the Planck temperature, the Planck length, the Planck time, are not arbitrary. They are stitched together from the most fundamental constants of nature, the speed of light, the gravitational constant, and Planck's constant from quantum mechanics. Together they mark the borderland where gravity and quantum effects are equally strong, where the smooth curves of Einstein's relativity crash into the jittering uncertainty of quantum physics. In that collision of descriptions, neither theory holds alone, and some new, deeper understanding is needed. Physicists have spent decades exploring candidates for this deeper theory. String theory with its hidden dimensions, loop quantum gravity with its woven networks of space-time, or ideas of gravitons, hypothetical particles carrying the force of gravity. None is proven, all are possibilities, and each promises to open the gate that Planck scales have set before us. It is a little like standing at the edge of a forest as evening falls. You can see the first line of trees, tall and dark against the fading light. Beyond them, shapes shift, and you cannot tell whether they are branches, animals, or shadows. You know there is something there, but your eyes cannot bring it into focus. The Planck limits are the first trees, the visible border. Beyond them lies the forest of quantum gravity, where our ordinary maps no longer work. And so, when we talk about the first instant of the universe, we must accept that we can only begin our walk after those gates, not before. We can describe the universe from about 10 to the negative 43rd seconds onward. Earlier than that, our best theories point and gesture but cannot explain. Yet this is not a failure. It is an invitation. Every scientific mystery begins with a boundary, a point where knowledge fades into wonder. When you sit tonight in your quiet room, imagine that you're standing at that boundary. Before you stretches not emptiness but possibility. The Planck scales mark the limit of our words, yet behind them lies the origin of all stories. Whether the universe sprang from a froth of foam, a field of strings, or a silence too deep for theory, we may never know for certain. But we know this much. After the Planck gates, the universe began to unfold in ways we can trace, from blazing temperatures down to the chemistry of life. And our journey through those steps will be like following footprints through sand, each one leading closer to the dawn. If you look around your life, you notice that forces have their own distinct personalities. Gravity pulls you down into your chair. Electromagnetism lets the lamp glow beside you. The strong nuclear force binds the protons and neutrons within every atom of your body. The weak nuclear force quietly operates in the background, responsible for certain kinds of radioactive decay. They are like 4 separate characters in the same play, each with its own role, each entering the stage in different costumes. Yet cosmologists believe that in the very early universe, long before atoms or stars or even light as we know it, these forces were not strangers at all. They were one. This idea is called grand unification, and it suggests that at energies far beyond anything we can achieve on Earth, 3 of the forces we see today, the strong, the weak, and electromagnetism, merge into a single, harmonious interaction. Only gravity remains apart, its relationship to the others still a mystery. But in those first moments after the Planck time, before the universe cooled enough for separation, the forces were indistinguishable, like colours blending together in a blinding white light. It can be difficult to picture such unity, because we are so accustomed to differences. Imagine a prism placed in a beam of sunlight. The light looks pure and simple, but the prism reveals that it is not one colour but many, spread into a rainbow. The early universe is the opposite. What we now experience as a rainbow of forces was once compressed back into the single brightness of an undivided state. In that undivided moment, particles too had no lasting identity. Protons, neutrons, electrons, the things we think of as the furniture of matter, did not yet exist. Instead, there was a fluid of fields and excitations, trading forms with ease. At these temperatures, a particle could transform into another, the way a melody shifts from one instrument to another in an orchestra. The notes the same, but the timbre different. You could say that matter was undecided about its future, or that it was generous, willing to be any possibility in the catalogue of physics. The strong force, which today is the glue inside atomic nuclei, was not yet distinct. Electromagnetism, which lets your phone buzz and your eyes perceive colour, was folded together with the weak force into what physicists call the electro-weak force. Above them all, at still higher energy, the strong and electro-weak would have blended too. The cosmic broth was in equilibrium, every interaction essentially speaking the same language. No accents, no dialects. When you stir a pot of soup on the stove, the flavours are mixed so thoroughly that no ingredient stands out. You cannot yet taste the carrot or the onion separately. All you know is warmth and salt. Only when the soup cools and you take a spoonful does each piece become recognisable again. In the same way, as the universe expanded and cooled, the superforces began to lose its homogeneity. The strong force split away first, leaving the electroweak behind. Later still, the electroweak itself would divide, electromagnetism on one side, the weak force on the other. With each split, the cosmos became more structured, less uniform, more like the world we know. But for a brief moment, everything was one. And that is not just a romantic thought, it is a clue carried within the mathematics of particle physics. Equations suggest that at extraordinary energies, the constants describing these forces converge. The lines on the physicists' graphs, representing the strengths of the different interactions, approach each other as though trying to meet. Some theories, such as supersymmetry, propose ways to make them meet perfectly. Others leave small gaps. Either way, the hint is tantalizing. The forces we treat separately today may once have been threads of a single rope. What would it have felt like to stand in that undifferentiated universe? Of course, no standing was possible. No solid ground, no atoms, no bodies to do the feeling. But if one imagines gently, it might have been like floating inside pure light, a brilliance without detail. There was no gravity pulling heavier things more strongly, no electricity sparking, no magnet pointing north. There was only interaction, total and seamless. The entire cosmos was less than a fraction of a second old, yet it already contained within it the seeds of variety, of separation, of the complex world that would emerge. The idea of unification has long appealed to human thought. Philosophers have sought unity behind diversity, a single principle beneath the many. In the natural world, we constantly look for patterns that tie things together. The early universe, it seems, truly embodied that desire. It was unity, not variety. It was a single note before the chord. And like a musical note allowed to resonate, it began to split, to develop harmonics, to create richness. There is also a poignancy in the fact that such unity cannot last. The universe, in cooling, lost its oneness. But that loss made everything else possible. If the forces had remained unified, the stable structures of atoms and molecules could not have emerged. Without the split, there would be no stars, no planets, no chemistry, no living beings. The shattering of symmetry was, in truth, a kind of gift. It was the universe giving itself away, breaking itself into pieces so that complexity could exist. Tonight, as you listen, perhaps you can imagine holding something simple in your hand, like a plain white stone. Its colour is uniform, its surface unremarkable. Yet if you could magnify it down to the atomic scale, you would see an extraordinary dance of protons, neutrons, electrons, forces pulling and pushing, differences creating structure. In the same way, behind the simple whiteness of the early universe lay the promise of structure, waiting to unfold. And so, the first step after the Planck gates was unity. The universe was a pure chord, a simple soup, a white light unbroken by prisms. But cooling brings change. The soup cannot stay hot forever. In the next moments, cracks appeared in the mirror of symmetry, differences emerged, and what was one began to become many. The cosmos was preparing for its next act. The universe, in its first breath, carried a kind of wholeness that is almost impossible for us to imagine. The forces of nature spoke the same language. Matter had not yet chosen its roles, and everything shimmered with a strange unity. But unity is a delicate thing. As the universe expanded, it cooled, and cooling brought change. What had been one began to split, not suddenly with a loud crack like glass breaking, but subtly, like ice crystals forming in a pond that had been liquid only moments before. Patterns emerged, differences appeared, and the grand symmetry of the early universe began to fracture. This process is known as symmetry breaking, and it is one of the quiet revolutions that shaped everything we see today. Symmetry in everyday life is something we find beautiful. We notice it in the balanced wings of a butterfly, in the even petals of a flower, in the reflection of our face in a mirror. When symmetry is broken, something changes. Imagine a perfectly balanced spinning top. As long as it spins smoothly, every side is the same. But the moment it wobbles and falls, one side touches the ground, another points to the air, and the symmetry is lost. In the universe, the loss of symmetry did not mean disorder, but rather the emergence of structure, the differentiation of roles. It was not a fall, but a transformation. In those first fractions of a second, the strong nuclear force peeled away first from the unified blend. This was the first crack in the mirror. The strong force, which today binds quarks into protons and neutrons, became distinct, leaving the other forces still fused together as the electroweak interaction. The cosmos was still unimaginably hot, still denser than anything we can reproduce, but already the seeds of difference were sown. The electroweak force lingered as a union for a while longer. Electromagnetism and the weak nuclear force were still one, their behaviours indistinguishable. But as the universe cooled further, another transition came. The electroweak symmetry shattered, and the two forces we know today, electromagnetism and the weak force, emerged. Photons, the carriers of light, went their own way, destined to be massless and free, while the particles that carry the weak force, the W and Z bosons, gained mass. This was the moment when the Higgs field settled into its role, a quiet but decisive moment we will linger on in our next chapter. To imagine symmetry breaking, think of a pencil balanced perfectly on its tip. In principle, it could fall in any direction. The laws describing the balanced pencil treat all directions equally. They are symmetric. But the pencil cannot remain balanced forever. It tips, perhaps to the left. The symmetry is broken, not in the laws themselves, but in the outcome. The universe, too, tipped. At its highest energies, all possibilities were equal. But as it cooled, one outcome was chosen over others, and the uniform wholeness fractured into a patchwork of distinct forces and particles. Another way to picture it is with water. When it's warm enough, water is liquid, smooth and shapeless. Cool it, and crystals of ice appear, their structures determined by hidden symmetries of molecules. The transition is dramatic but quiet, like a new pattern emerging from an old fabric. The early universe was going through a series of such phase changes. Each change reduced its symmetry, but in doing so it increased its richness. The physics of symmetry breaking is subtle, but the consequences are vast. Without these transitions, particles would not have mass, atoms would not form, and stars could not burn. The world we live in, its chemistry, its structures, its very possibility, depends on the universe choosing, in those early instants, to break its initial symmetry. What we might think of as cracks in the mirror were, in truth, the first brushstrokes on the cosmic canvas. It is tempting to ask, why those breaks, and not others? Why did the universe choose this particular way of falling, this particular set of forces and particles? The equations allow many possibilities. Perhaps it was chance, a quantum coin toss at the dawn of time. Perhaps it was necessity, an inevitable consequence of the fields that existed. Or perhaps it was one outcome among many, with other universes elsewhere in a vast multiverse falling in different directions, breaking symmetry differently, creating worlds with laws we cannot imagine. These questions are not answered, and maybe they never will be. But part of the beauty of symmetry breaking is that it does not require us to know why it happened in order to marvel at what followed. Imagine standing before a frozen lake in winter. You see the cracks in the ice, branching patterns across the surface. You do not need to know the exact sequence of stresses that formed them to recognize their beauty. In the same way, we can look at the separation of forces, the tipping of the universe into difference, and recognize the strange elegance in its unfolding. As you listen, tonight you might reflect on how breaking can sometimes create possibility. A seed splits its shell to become a tree. A cloud breaks open to release rain. A heart, even when broken, can open to new forms of love. The universe itself is born of such breaking, of unity giving way to diversity, of perfection cracking into the imperfect richness that makes life possible. Symmetry. Breaking is not the loss of harmony, but the transformation of it, the emergence of a deeper music hidden within the silence. So in that first second, after the Planck limits, after the brief period of unification, the universe cooled enough to fracture. Forces split apart, particles began to take on their identities, and the mirror that once reflected only sameness now reflected a world of differences. These cracks were not flaws. They were the openings through which everything else would flow, the galaxies, the stars, the chemistry of life, and even the quiet moment you spend listening now. When you look at the world around you, everything has weight, heft, resistance. You lift a mug, you feel the mass in your hand. You walk across the floor, and each step has a sense of gravity, of presence. It is so ordinary that it feels unquestionable, yet in the earliest instance of the universe, mass itself did not exist in the way we know it now. Particles were not burdened with weight. They moved as though in a perfect vacuum, zipping freely without resistance. For a short time, the universe was populated by ghosts, entities without substance, without inertia. It was only when a peculiar field awoke, filling all of space with its invisible influence, that matter became tangible. That field is known as the Higgs field, and its arrival is sometimes described as the moment when the universe gave matter its body. The Higgs field is difficult to picture because it is everywhere, woven into the fabric of reality, yet unseen. A common analogy is to imagine a room filled with molasses, thick and sticky. As particles try to move through this molasses, some are slowed down more than others, and that slowing is what we call mass. Photons, the particles of light, glide through untouched, remaining massless, able to race at the cosmic speed limit forever. But W and Z bosons, the carriers of the weak nuclear force, interact strongly with the Higgs field. They become heavy, acquiring the inertia that allows the weak force to have the peculiar character it does. Quarks and leptons, the building blocks of protons, neutrons and electrons, also interact and thus gain their weight. Without this invisible molasses, the universe would be filled only with massless particles rushing endlessly, unable to clump, unable to form atoms, stars, or you. A softer way to imagine it is to picture a ballroom. The Higgs field is the crowd gathered inside. Some dancers move easily across the floor, slipping past unnoticed. They remain light, barely affected. Others attract attention. The crowd clusters around them, slowing their passage. They become heavy. In this analogy, the dancers are particles, and the crowd is the Higgs field. Photons move like unnoticed guests, slipping past. Quarks and W bosons are celebrities, mobbed wherever they go. The difference between light and heavy particles is not intrinsic to them alone, but arises from their interaction with the ever-present crowd. The appearance of the Higgs field was itself a kind of symmetry breaking. The electroweak force, which once carried both electricity and the weak interaction together, split apart because of it. Before the Higgs field settled into its non-zero value, the world had a higher symmetry, more uniform but also sterile. Once the field chose its ground state, symmetry cracked, and the weak force gained its heavy mediators while light kept its photon. You might think of it as a meadow filled with tall grass bending all in the same direction once the wind decides to blow. Before the bending, every direction was equivalent. Afterward, one direction is special, and the uniformity is gone. Yet in that loss, new structures and possibilities emerge. This was not a gentle change, but a cosmic phase transition, like water turning into ice, only at unimaginable energies. For a brief instant, the universe was filled with a kind of Higgs condensate, a new property of space that would never again disappear. Once awakened, the Higgs field remained, stretching across all of space and time, silently maintaining the masses of particles everywhere. Every object you touch, every atom that holds your body together, owes its substance to this ancient transition. We did not confirm the existence of the Higgs field until 2012, when the Large Hadron Collider at CERN produced the Higgs boson, the particle linked to the field. Scientists called it the God particle in popular media, though the nickname was misleading. It is not divine, but rather deeply practical, a confirmation that our theory of how particles gain mass was correct. Still, it is striking to realise that this quiet field, invisible and constant, has shaped the universe for nearly 14 billion years, while only recently did we find clear evidence of its existence. To imagine life without the Higgs is to imagine a universe that never thickened into substance. Particles would flit endlessly like sparks without ash, never gathering, never condensing into matter. Without mass, gravity would have nothing to tug upon. Stars would not ignite, planets would not form, and chemistry would not exist. The Higgs field is the silent stagehand behind the cosmic performance, pulling curtains and arranging props without ever stepping into the spotlight. In a more poetic sense, the Higgs represents the moment when the universe grew a skeleton. Before, it was vaporous and insubstantial. After, it had bones, framework, structure. The play could now begin in earnest. The quark era followed, in which the fundamental building blocks of protons and neutrons could hold together. Soon after came the first nuclei, then the atoms that would one day shine as stars. The Higgs was not the end of the story, but without it, the story would have been only empty light. A book of blank pages. Tonight, as you sit in your room, you are surrounded by evidence of this invisible field. The weight of the blanket on your legs, the firmness of the floor beneath your feet, the warmth of the body you inhabit, all of it is mass, given to matter by the Higgs. You do not see it, yet you feel it every moment of your life. The field does not ask for thanks. It is like the background hum of a fan, unnoticed until someone points it out, but always shaping the texture of the room. So in that first second, amid the cooling and the breaking of symmetries, the Higgs awakened. The universe clothed its particles in mass, dressed them in weight, and prepared them for the work of building worlds. The awakening was invisible, yet it gave substance to everything. It was a whisper that turned into a foundation, a soft unfolding that changed the course of reality. And from that point onward, matter was no longer a dream. It was real, tangible, ready to shine. When you step outside on a cool evening and look up, the night sky seems endlessly varied. Stars sparkle with different colours, galaxies lie at different distances, and the moon casts its silver glow in one corner. It feels uneven, full of contrast and detail. Yet when astronomers measure the universe at the larger scales, when they look not at individual stars but at the overall glow of the cosmos, they find something almost unnervingly smooth. The cosmic microwave background, that faint afterglow from the early universe, is nearly identical in every direction. One patch of sky looks like another, warmed to within a few tiny fractions of a degree. It is like walking into a cathedral and finding that every stone has been carved with almost the same pattern, despite being scattered across vast distances. This smoothness presents what scientists call the horizon problem. Imagine two children sitting on opposite sides of a playground, each holding a thermos of hot chocolate. If they never meet, never exchange a word, never pour their drinks together, you would expect the cocoa inside each thermos to cool at its own pace. One might be lukewarm, the other piping hot. Yet when we look at regions of the sky that could never have communicated in the first few 100,000 years, their cocoa is at the same temperature. How did these separated regions manage to agree so perfectly? In the language of physics, how did parts of the universe beyond each other's horizon end up so uniform? Closely linked is the flatness problem. The universe appears to be balanced on a razor's edge. Space is neither curled tightly in on itself like a ball, nor flared outward like a saddle. Instead, It is astonishingly close to flat, as if stretched, taut. But this flatness is unstable, like balancing a pencil on its tip. Any slight departure from perfect balance in the early universe should have grown into enormous deviations by now. And yet, billions of years later, the cosmos is still poised delicately. Why did the universe begin so finely tuned? And then there is the mystery of magnetic monopoles. According to many theories of the early universe, exotic particles with a single magnetic charge, north without south, south without north, should have been produced in abundance. Yet in all our experiments and all our observations, not a single one has been found. The universe seems empty of them, though the equations suggest they should be common. It is as though the recipe listed them as an ingredient, yet the finished dish shows no trace. These puzzles, horizon, flatness, monopoles, were the cosmic riddles of the late 20th century. They were frustrating because the Big Bang model explained so much so well, yet left these odd contradictions. The universe was smooth where it should have been patchy, balanced where it should have been unstable, clean where it should have been littered with magnetic relics. Something was missing in the story. To picture the difficulty, imagine baking a loaf of bread. You mix flour, water, yeast, and salt, knead it, and place it in the oven. When it rises, you expect it to swell evenly, only if you mixed it thoroughly beforehand. If you had added clumps of flour in one corner of the bowl and left other patches watery, the loaf would come out uneven, lumpy in places, dense in others. Yet the cosmic loaf, the universe itself, emerged astonishingly smooth. The ingredients somehow mixed with perfect thoroughness, even though distant parts of the dough never had a chance to meet. The flatness problem adds to this picture. It is as if the loaf were not only smooth but also balanced exactly in shape, not slumping to one side, not bulging upward, but resting in perfect symmetry on the pan. And the monopole problem. That is like opening the oven and finding no burnt clumps, no lumps of unmixed ingredient, none of the relics you expected from messy chemistry. For cosmologists, these questions were more than curiosities. They were signs that the early universe was stranger than the original Big Bang picture suggested. Observations whispered that something had happened in those first fractions of a second, something that smoothed the soup, stretched the fabric, and erased the unwanted lumps. But what could possibly do all of this at once? The answer would come in the early 1980s, when a young physicist named Alan Guth proposed the idea of cosmic inflation. The details of inflation will be our focus in the next step of our journey, but its spirit can be grasped even now. A moment of extraordinary expansion, a swelling of space itself at speeds far beyond anything we see today. Inflation could explain why regions of the universe look so similar. They were once close together before being driven apart. It could explain why the cosmos is flat. Any curve would have been ironed out like wrinkles smoothed from a sheet. It could explain why magnetic monopoles are absent. Any relics were diluted to near non-existence, spread so thinly that not a single one remains in reach. The problems of horizon, flatness, and monopoles, though technical, are really about the same theme. How did the universe become so even, so balanced, so tidy? Without inflation, these traits are inexplicable. With inflation, they are natural consequences of a universe that stretched almost unimaginably in a heartbeat. When you picture it, do not imagine fireworks or explosions. Instead, think of bread rising in an oven. The yeast pushes the dough outward in all directions at once, smoothing out inconsistencies, creating a loaf that is evenly puffed. Or imagine a balloon inflating so quickly that any marks drawn on its surface are swept apart until they appear flat. Inflation does not just solve problems, it reframes them. What seemed improbable becomes inevitable when you imagine the universe expanding by such an enormous factor. For now, though, let us hold on to the puzzles themselves. They are reminders of how delicately tuned the cosmos is, how finely balanced. If you feel small beneath the stars, remember that even the stars themselves owe their existence to a balancing act that began in the first second. The universe did not simply explode into being, it stretched, smoothed, and refined itself in ways that still astonish us. Inflation is the answer we will explore next, but the questions, the horizon problem, the flatness of space, the missing monopoles, are what made scientists look deeper. And in those questions, as much as in the answers, lies the beauty of cosmology. In everyday life, expansion is usually a slow affair. A tree stretches upward over years, a loaf of bread rises gently in the oven, clouds drift wider across the sky. We're accustomed to growth that takes its time, growth that we can watch unfold. But in the early universe, expansion was not slow and patient. It was sudden, dramatic, and almost beyond our ability to picture. In the smallest fraction of a second, space itself ballooned outward, carrying everything within it along for the ride. This is the idea of cosmic inflation, and it is one of the most powerful and strange concepts in modern cosmology. Inflation describes a moment when the universe grew not by a factor of 2 or 10, but by at least 90 e-folds, a phrase that means it doubled in size more than 90 times in rapid succession. If you start with something the size of a proton and double it 90 times, you end up with something larger than the observable universe today. All of this happened in less than the blink of an eye, faster than thought, faster than light could even cross a single atom. It is not that matter was moving through space faster than light, rather space itself was stretching, expanding at a rate unconstrained by the cosmic speed limit. The result was a cosmos suddenly vast, smooth, and set on the path to become what we now see. It is difficult to imagine such sudden swelling, so let us reach for metaphors. Imagine ripples on a small pond. At first they are tiny, disturbances spreading in delicate circles. Now imagine that the pond suddenly swells into an ocean, the ripples stretched into mighty waves, visible across vast distances. The tiny fluctuations that once existed at microscopic scales during inflation were expanded in this way, magnified to cosmic proportions. Later, under the pull of gravity, those stretched ripples would seed galaxies, clusters, and the great cosmic web. What began as quantum tremors became the scaffolding of everything. Another image is a balloon covered with specks of dust. When the balloon is small, the specks lie close together. Blow into it, and they are swept apart. If you inflate the balloon by a few breaths, the specks are still visible to each other, still connected by proximity. But if the balloon inflates exponentially, in a sudden burst, the specks rush apart so quickly that they no longer share any connection. Inflation carried every region of space away from its neighbours in exactly this way. Regions that had once been in contact, sharing energy and temperature, were pulled so far apart that they now lie billions of light years from each other, appearing mysteriously uniform because they were once close before inflation flung them apart. Inflation is more than an elegant story. It is a solution to the riddles we considered in the last session. The horizon problem vanishes when you realise that distant regions of space were once neighbours. The flatness problem is solved because inflation smooths out curvature just as stretching a small patch of paper flattens its wrinkles, and the missing monopoles are explained because any exotic particles that once existed were spread so thinly that they became essentially invisible. Inflation acts like a great cosmic ironing board, pressing the fabric of the universe smooth, even, and nearly perfect. But inflation is not just about smoothing, it is also about seeding. During that brief moment, quantum fields were bubbling with fluctuations, the unavoidable jitter of the quantum world. Ordinarily, these jitters are tiny, almost imperceptible, but inflation took them and magnified them, stretching them into density variations in the fabric of space. Where there was a little more density, gravity would later tug matter into galaxies. Where there was a little less, voids would open. The grand structures of the cosmos were, in a sense, written into the randomness of quantum uncertainty, amplified to astronomical scales. It is as if the tiniest tremors in your hand as you write a letter were expanded until they became mountain ranges on the page. Alan Guth, the physicist who first proposed inflation in 1980, once described it with a mixture of awe and humility. He had been working on problems in particle physics, trying to understand why the universe lacked magnetic monopoles, when he stumbled onto the idea that an unstable field could release energy by driving rapid expansion. The more he worked, the more he realised that this wild idea did not just solve one problem, but several at once. It was as though a key meant for one door suddenly opened an entire hallway. Since then, inflation has become central to cosmology, though it is still a theory in need of deeper proof. Observations of the cosmic microwave background show the faint fingerprints of inflation in the way its tiny variations are distributed. The specific spectrum of those fluctuations matches what inflation predicts. Still, the exact mechanism, what field drove the expansion, how it ended, whether it could happen again, is unknown. Like many ideas in cosmology, it is both powerful and provisional, a story that fits the clues we have but leaves many blank spaces. To bring it closer to daily life, imagine kneading dough before baking. At first it is lumpy, irregular. But as you stretch and fold it, it becomes smoother, air pockets distributed evenly. Inflation was like that, but on an unimaginable scale. In less than a whisper of time, the dough of the universe was kneaded, stretched, folded, and made ready for baking into stars, galaxies, and life itself. If you pause for a moment now, you can almost picture it. A cosmos that began as something tiny, flickering with quantum energy, suddenly expanding into a vastness we can hardly comprehend. Not an explosion in space, but an expansion of space itself, unfolding silently, invisibly, irresistibly. Inflation is one of the most audacious ideas science has ever proposed, and whether or not we know every detail, it offers a vision of beginnings that is at once profound and strangely comforting. For it tells us that even the smallest tremors can grow into something vast, that a whisper of quantum uncertainty can blossom into galaxies, and that the smoothness we see in the night sky is the legacy of a brief, impossible expansion that set the stage for everything to come. When cosmic inflation ended, the universe found itself in a peculiar state. Space had stretched by an almost absurd factor, smoothing itself out like dough rolled flat, ironing away wrinkles and irregularities. But this sudden stretching did not immediately leave behind a lively, particle-filled cosmos. Instead, the energy that drove inflation was still trapped in a kind of vacuum-like field, silent and austere, a universe vast but nearly empty, stretched thin and waiting. The next step was to fill it with substance. This is the story of reheating, a moment when stored energy poured back into matter and radiation, flooding the universe with the ingredients of everything to come. Reheating may sound like a return to warmth after cooling, but in truth the universe never stopped being hot. It was more like a stove that had been turned on without food in the pan. Energy was there, humming, but not yet transformed into a meal. When inflation ended, that energy was released into a storm of particles, a seething broth of quarks, leptons, photons and gluons, all colliding at temperatures trillions of times higher than the core of a star. What had been an eerie emptiness suddenly became the most crowded party imaginable. A dance floor filled wall to wall with jittering dancers, each jostling and exchanging partners in constant motion. The term reheating comes from the idea that after inflation's strange phase, the universe had cooled relative to the furious temperatures of earlier instants. But once energy poured back into particles, the heat soared again. Imagine a snow globe shaken vigorously. At first the flakes are pressed against the glass, stuck by static and stillness. Then you shake it, and the flakes explode into motion, filling every corner with shimmering activity. Reheating was that shake, an instant of release when trapped energy scattered into a million directions, filling the emptiness with light and matter. The details are technical, bound up with questions about what field drove inflation and how it decayed. Physicists speak of oscillating inflaton fields, decays into bosons and fermions, cascades of interactions. But you need not memorize the jargon to feel the essence. The energy that inflated the universe was unstable, and like water behind a dam, it eventually spilled over. When it did, the flood created the first genuine population of particles, the beginnings of a universe we can recognize. Reheating also marked the beginning of chaos in the best sense. Before, the universe was eerily smooth, an empty canvas. Afterward, it was turbulent, noisy, alive. The soup of particles was dense enough that interactions happened constantly. Quarks smashed into each other, exchanging gluons, occasionally binding in fleeting partnerships. Leptons darted about, lighter and more aloof. Photons bounced off charged particles, scattering so much that light could not yet travel freely. Space was not dark or light, but opaque, like the inside of a furnace where sparks cannot escape the flames. It is worth pausing to notice how different this picture is from the phrase Big Bang, which conjures images of fireworks and bright explosions. The actual birth of the universe was more subtle, more like the slow opening of a vast oven door, heat flooding outward into a room that had been waiting. There was no outside into which the blast could expand. Space itself was the oven, and the heat belonged everywhere at once. Reheating gave that oven its first filling, its first true mixture of ingredients, though the recipe was still simple: quarks, gluons, leptons, photons. From these few came everything. To imagine the intensity, consider how energy is transformed in more familiar settings. In a thunderstorm, charged particles and clouds release energy as lightning, a flash that lasts a fraction of a second. In a power plant, nuclear reactions release energy steadily, producing electricity for years. Reheating was like both at once, sudden like lightning, steady like nuclear fire, but magnified to scales beyond comprehension. In a single cosmic instant, energy became substance, light, and motion. One of the remarkable things about this moment is how it set the stage for balance. Too few particles, and the universe would have remained thin, too empty for stars to gather. Too many, and it might have collapsed quickly under its own weight. The reheating process, whatever its details, produced just the right density. A universe that would expand steadily, but not scatter its contents into nothingness. That delicate balance is why galaxies could one day form, why chemistry could one day unfold, why you can sit here now with air in your lungs and warmth in your hands. In laboratory experiments, physicists attempt to recreate echoes of these conditions. At the Large Hadron Collider, protons collide at nearly the speed of light, producing showers of particles that mimic, in miniature, the frenzy of the early universe. These collisions give us a glimpse into what reheating might have felt like. A sudden burst of transformation, order emerging from chaos, fleeting new particles appearing before dissolving again. Of course, no collider can reproduce the sheer scale of the cosmos. What we see in those detectors is like watching sparks fly from a campfire, while the real event was a wildfire raging across the entire universe. If you wish for a gentler analogy, think again of the snow globe. Before you shake it, the flakes are settled, the scene inside quiet but lifeless. After the shake, every corner is filled with motion, flakes tumbling, glinting, colliding. The difference is dramatic but also beautiful, for without that motion, the globe is only an ornament. It is the dance of the flakes that makes it alive. Reheating gave the universe its dance, its shimmer, its first true vibrancy. Tonight, As you drift between waking and sleep, you might picture that moment not as something violent, but as something strangely peaceful. Energy flowing into matter, space filling with light, the stage finally furnished with actors who could play their roles. The cosmos had expanded, it had smoothed itself, and now it was ready to begin its performance in earnest. Quarks, leptons, photons, all the simplest dancers were present, spinning and colliding in an endless ballet. From this dance, in time, would come atoms, stars, planets, and consciousness itself. Reheating was not the end of creation's story, but the first movement of its symphony, the moment the music began to play. After reheating, the universe was no longer a stretched emptiness. It had become a roiling ocean of particles, a dense and furious broth that filled every corner of space. Physicists call this state the quark-gluon plasma, a name that sounds technical but can be pictured more simply as a kind of primordial soup. Within it swam quarks, the most fundamental building blocks of protons and neutrons, held together and torn apart by gluons, the carriers of the strong force. For the first microseconds after the Big Bang, this soup dominated everything. The temperature was still beyond anything we encounter today, trillions of degrees. At such heat, ordinary matter could not exist in familiar forms. Protons and neutrons could not yet hold together. They dissolved in the intensity, their ingredients set free to mingle wildly. The quark-gluon plasma was more like a storm than a calm sea, with currents and eddies colliding constantly, particles smashing together and parting again in endless motion. To bring it closer to life, imagine a crowded dance floor at the peak of a celebration. The room is packed so tightly that dancers can hardly move without bumping into one another. Every gesture ripples through the crowd. Every turn causes a dozen collisions. You cannot follow a single dancer for long before they vanish into the crush. The quark-gluon plasma was like that dance floor, filled with jittering energy, collisions happening faster than any eye could track. The difference is that these dancers were not couples in gowns and suits, but the tiny quarks that would one day form the backbone of all matter. What makes this state so fascinating is that it was universal. Today, quark-gluon plasma is something we create only rarely, in massive experiments like those at the Large Hadron Collider or the relativistic Heavy Ion Collider in the United States. By smashing together heavy ions at near-light speeds, physicists briefly recreate droplets of that ancient soup. For a fleeting instant, detectors see quarks and gluons moving almost freely, echoing the conditions of the universe's first microseconds. But in the early cosmos, this was not rare. It was everywhere. The natural state of existence. The strong nuclear force carried by gluons is the most powerful force known in nature. It binds quarks together so tightly that protons and neutrons are almost impossible to tear apart. Yet at the temperatures of the early universe, the strength of the force was overcome by sheer energy. The gluons still darted among quarks, but instead of locking them firmly in pairs and triplets, they allowed quarks to flow in a liquid state, like dancers holding hands for a moment before spinning off again. The soup had no fixed structure, only constant exchange. Over time, though still within the first millionth of a second, the universe cooled enough that this wild freedom began to settle. Quarks started to become confined, pairing and tripling into protons and neutrons. The dance floor, while still busy, developed cliques and groups. Where before every dancer had bumped into every other, now certain partners clung together more tightly, refusing to part. These pairings were not arbitrary. The mathematics of the strong force demands that quarks combine in very specific ways, in groups of 2 or 3 that neutralize their color charge. The result was the first stable composite particles, the ingredients that would later build atoms. It is tempting to imagine this transition as sudden, but it was gradual, like a pot of soup cooling on the stove. At first, everything is boiling, ingredients churning without distinction. Slowly, patterns emerge, bits settle, flavours combine, the chaos becomes something recognisable. The early universe went through just such a cooling, transforming the plasma into matter with structure. Another image might be of mist condensing into raindrops. The vapour is everywhere, shapeless, but as the air cools, droplets form. Quarks are the mist. Protons and neutrons are the droplets. Once droplets form, they can fall, gather, and eventually form rivers and oceans. Likewise, once protons and neutrons formed, the way was paved for nuclei, atoms, molecules, and all of chemistry. The quark-gluon plasma was a necessary prelude, but it could not last forever. Physicists sometimes call this era the quark epoch, though that phrase does not quite capture the dynamism of the scene. It was not a time when quarks ruled serenely, but when they tumbled, clashed, and merged in a frenzy. The music of the cosmos was fast and loud, a symphony of collisions echoing across every speck of space. Yet from that frenzy came stability. In cooling and condensing, the universe prepared itself for the next steps, the delicate balance between protons and neutrons that would shape the chemistry of stars. When we study quark-gluon plasma in particle colliders today, we are not only probing the physics of small particles, we are glimpsing our own origins. The very atoms in your body, the carbon in your cells, the iron in your blood, the calcium in your bones, are made of protons and neutrons whose quark ancestors once swam in that primordial soup. Every human, every star, every grain of dust carries a memory of the crowded dance floor, the storm of particles that defined the first instance. And so, the universe passed from silence into fury, from a stretched vacuum into a boiling sea. For a millionth of a second, quarks and gluons rushed and collided, a chaos that was both violent and essential. Without it, there would be no matter. Without matter, no galaxies. Without galaxies, no stars. Without stars, no life. That frantic dance, so short in time, left an imprint that endures in every corner of existence. Tonight, as you listen in the quiet, picture that sea, not with fear, but with wonder. Imagine the room around you filled with a soft golden fog, particles moving everywhere, brushing past one another, never still. In that fog lies the promise of structure, the promise of form, the promise of the universe you know. The storm of quarks and gluons was not chaos for its own sake. It was the necessary turbulence from which calm could emerge, the first restless heartbeat of matter becoming real. As the fiery quark-gluon sea cooled, something delicate began to happen. The furious dance of quarks, gluons and leptons settled just enough for order to emerge. Protons and neutrons, the first true building blocks of matter, began to hold together. This moment, though it lasted only a fraction of a second in cosmic terms, determined the recipe of the universe. Too many protons and not enough neutrons, and the stars would later burn differently, producing a chemistry unlike our own. Too many neutrons and too few protons, and the cosmos would be a place of heavy, unstable nuclei, quick to decay, unable to form the gentle mix of hydrogen and helium that seeds life. The balance was fragile, and yet it was struck in a way that seems almost miraculous. At around 1/1,000,000th of a second after the beginning, the universe cooled to a temperature of about 1,000,000,000,000 degrees. This was still unimaginably hot, but no longer hot enough to keep protons and neutrons from forming. Quarks began to lock into trios, bound tightly by the strong force into these heavier particles. The dance floor of free quarks gave way to a gathering of structured partners, the first stable groups in a universe that had known only chaos. But protons and neutrons were not created in equal numbers. Subtle differences in the physics of their interactions led to a slight preference. Neutrons are a bit heavier than protons, and as the universe cooled, processes that turned neutrons into protons became more common than those that turned protons into neutrons. The result was a freeze-out ratio of about 7 protons for every neutron. This ratio may sound like a small detail, a footnote in cosmic history, yet it is one of the most consequential numbers ever written into nature. To grasp its importance, think of baking bread. The proportions of flour, water, and yeast must be just right. Too much flour and the loaf is dry and crumbly. Too much water and it collapses into a gooey mess. A balanced recipe creates something edible, nourishing, even beautiful. The universe's recipe was written in this 7-to-1 balance. That ratio meant that when the first nuclei formed minutes later, there would be enough protons to create abundant hydrogen and enough neutrons to fuse into helium, but not so many that the cosmos would become weighed down with heavier, unstable elements. The neutron-proton balance also mattered for survival. Neutrons by themselves are unstable. Left alone, they decay within about 15 minutes. But if they are bound together with protons inside a nucleus, they can persist for billions of years, stable as the atoms that make up your body. By fixing the ratio at 7-to-1, the universe guaranteed that enough neutrons would survive long enough to form helium, while most of the matter remained in the form of protons, destined to be hydrogen. Without that ratio, hydrogen, the fuel of stars, might have been scarce, and the story of the cosmos would have unfolded very differently. It is worth pausing to consider the humility of hydrogen. It is the simplest of all atoms, a single proton, often with a single electron orbiting it. Yet simplicity does not mean insignificance. Hydrogen is the raw material of the stars, the fuel for the furnaces that will one day cook heavier elements. Helium, born of the captured neutrons, adds stability and beauty, glowing in stars and filling balloons on Earth. That gentle 7-to-1 balance created a cosmos with both oceans of hydrogen to ignite stars and enough helium to stabilize them and help them shine. Physicists sometimes describe this ratio with the cool language of cross-sections and decay rates, but one can also describe it more softly. It is as though the universe was mixing paints on a palette, blending reds and blues to just the right hue. Too much red and the canvas would glare, too much blue and it would darken into gloom. The final shade was balanced, delicate, perfectly poised to paint galaxies and worlds. Even now, billions of years later, we see the outcome in the skies. About 3/4 of the ordinary matter in the universe is hydrogen, and about 1/4 is helium. That proportion traces directly back to the neutron-proton balance set in the first second. Every breath you take is mostly hydrogen that has been cycling through stars, clouds, and planets for eons. Every helium atom released from a balloon at a birthday party is a direct descendant of neutrons frozen into nuclei moments after the Big Bang. The party decoration and the cosmic furnace both carry the same ancestry, the same balance struck in the earliest instant. The fragility of this balance also hints at how finely tuned our universe is. Had the ratio been even slightly different, stars might have lived shorter lives, or heavier elements might never have formed. Chemistry as we know it, with carbon, oxygen and nitrogen, might not exist. Life might not exist. The difference of a single neutron in a billion protons was enough to tip the outcome towards stability. It is a reminder that great consequences can hinge on tiny asymmetries, that the shape of the cosmos can depend on something as small as a fraction. Tonight, as you listen in the calm, consider that the atoms in your body carry this signature. The hydrogen in the water you sip before bed, the helium that lights neon tubes in a quiet diner sign, the fuel of the stars that glimmer faintly through your window. All of it flows from that ancient freeze-out, when the universe cooled enough for protons and neutrons to settle into their roles. That 7-to-1 balance is not just a number on a chalkboard. It is a whisper from the first second, telling us that order emerged from chaos, that recipes were written long before life learned to cook, that proportions mattered even before planets and oceans, and hearts began to beat. The dance of quarks was frantic, the plasma was stormy, but from that storm emerged a balance as gentle as a scale settling evenly. One side dipped just slightly lower, and in that dip lay the future of galaxies and life. The protons and neutrons, locked in their fragile ratio, became the foundation of chemistry, of stars, of you. And in the silence of the night, it is worth remembering that balance, struck in fire, yet enduring in every breath. Every story of creation seems to carry with it a shadow, a counterpart that mirrors the hero but does not survive. In the story of the universe, that shadow is antimatter. For every kind of particle that makes up the world around us, electrons, protons, neutrons, there exists a partner of opposite charge, like a twin who is reflected in a mirror but cannot share the same space for long. Electrons have positrons, protons have antiprotons, neutrons have antineutrons. The rules of quantum fields say that particles and their opposites must always be created together, pairs appearing from the fabric of energy like dancers stepping hand in hand onto a stage. In the first instance after reheating, the universe was a ballroom filled with such pairs. For every proton there was an antiproton, for every electron a positron. The numbers were nearly exact, as if nature had insisted on keeping the books balanced. Whenever a particle met its antiparticle, they annihilated, disappearing in a flash of pure energy. The dance was brief and often fatal. Partners twirled, collided, and dissolved back into light. If the universe had remained perfectly balanced, matter and antimatter would have cancelled one another completely, leaving behind nothing but radiation, a cosmos filled only with light, never able to form stars, planets, or life. And yet here we are. The room you sit in, the breath you draw, the earth beneath you, the galaxies overhead, all are made of matter. Antimatter exists only fleetingly, in cosmic rays, in rare radioactive decays, and in laboratories where physicists coax it into being for a moment before it vanishes. Somehow, in that ancient ballroom, matter won. For every billion particle-antiparticle pairs, one lonely extra particle of matter survived. When the rest annihilated into energy, those survivors remained, and they are the ancestors of all the atoms in existence today. This asymmetry is one of the deepest mysteries in physics. Why did the scales tip ever so slightly in favour of matter? The equations of the known forces seem to treat matter and antimatter symmetrically, as though both should have equal right to exist. And yet something broke that perfect balance. Physicists call this phenomenon CP violation, a small but measurable difference in how matter and antimatter behave. In experiments with kaons and B-mesons, subatomic particles produced in accelerators, researchers have seen that matter and antimatter do not decay in exactly the same ways. The imbalance is tiny, but in the early universe, even a tiny preference could snowball into dominance. Still, the amount of CP violation observed in laboratories does not seem large enough to explain the overwhelming presence of matter today. This leads to the possibility of deeper mechanisms. One idea is that heavy right-handed neutrinos, particles that we have not yet observed directly, may have decayed in ways that favoured matter over antimatter. These hypothetical neutrinos would have existed only in the first instant, vanishing long before galaxies, but their brief preference may have tilted the cosmic scales. Like a referee who secretly favours one side, their bias might have been small but decisive. To bring the image closer to life, think of a seesaw in a playground. Imagine a billion children seated on one side and a billion children on the other, perfectly balanced. Now add one extra child to the left. The seesaw tips. Slowly at first, but inevitably the imbalance grows noticeable. That single child determines the direction of the tilt. In the universe, the single child was that one extra particle of matter in every billion pairs, and that slight lean was enough to decide the fate of everything. Another way to picture it is to imagine a recipe that produces equal parts sweet and bitter. If they truly cancelled, the dish would taste like nothing at all. But if you add just a pinch more sugar, the sweetness wins and the dish has flavour. The universe's recipe contained a pinch more matter than antimatter, and because of that, flavour exists at all. The flavour of stars burning, of atoms bonding, of life unfolding. Even now, antimatter continues to fascinate us. In hospitals, positrons are produced for PET scans. Their annihilations mapped to create images of the human body. In particle accelerators, antiprotons are captured for a fraction of a second to test fundamental symmetries. In cosmic rays striking Earth's atmosphere, positrons appear as brief sparks of the ancient dance. These glimpses remind us that antimatter is not gone entirely, but it is rare, like the fading notes of a song that once played at full volume. The Great Disappearance was not gentle, it was annihilation on a scale we can barely comprehend. Oceans of particles and antiparticles collided and vanished in flashes of radiation, the energy flooding into the cosmos that still glows faintly today as the cosmic microwave background. Yet from this destruction came survival. Out of billions, one survived. That one in a billion is the reason there are mountains, oceans, birds, music, and quiet nights. That imbalance is why you can listen to this story at all. It is humbling to realise how precarious this victory was. Had the balance been exact, the universe would be a sea of light without substance, radiant but empty. There would be no atoms to form clouds, no stars to cluster into galaxies, no hands to build telescopes, no minds to wonder. Existence as we know, it rests on a fraction of a fraction, a cosmic coin toss whose outcome leaned ever so slightly toward matter. So as you settle deeper into the calm of this night, imagine that ancient ballroom once more. Pairs of dancers whirl across the floor, each with its mirror partner. Most of them collide and vanish in sparks of light, their music fading. But a few remain, matter without partners, the lone survivors of a great annihilation. They step to the centre of the floor, carrying forward the rhythm, the melody, the possibility of a universe. From their survival came galaxies and stars. From galaxies and stars came planets, and from planets came you. A universe born of disappearance, of imbalance, of a single grain tipping the scale. The universe's early moments were loud in their own way, dense, hot, crowded with collisions, a chaos of particles constantly scattering, annihilating and forming again. Every particle seemed to be talking to every other, exchanging energy like guests at a bustling celebration, a party so crowded you could not move without brushing against someone. In this cosmic party, neutrinos were among the guests. At first they mingled with ease, exchanging energy with electrons, positrons and other light particles. But within the first second, as the universe cooled and expanded, neutrinos began to slip quietly away. They decoupled from the crowd, stopped colliding, and went their own way, leaving behind a faint but eternal echo known as the cosmic neutrino background. To understand the subtlety of this moment, think of a crowded room filled with conversation. At first, every person is engaged, voices overlapping, ideas bouncing back and forth. But eventually some guests grow tired of the noise, step into the hallway, and wander into the night. They are no longer part of the chatter, yet the memory of their presence lingers. Neutrinos did something similar. For the first second of cosmic time, they were in constant communication with other particles, exchanging energy in the dense plasma. Then, as the universe expanded and cooled, the density dropped. Collisions became less frequent, and neutrinos slipped away, no longer held in the fray. Neutrinos are elusive by nature. Even today, trillions of them stream through your body every second, most of them born in the nuclear furnaces of the sun, others from cosmic rays striking the atmosphere, a few from distant supernovae. They interact so rarely that they pass through planets, walls and people, as though we were not even there. Imagine a stream of ghosts walking through a bustling city, invisible and untouchable, continuing on their paths without ever stopping at a door or waiting at a light. That is the life of neutrinos, and in the first second they claimed it fully. Their decoupling was not a dramatic exit. There was no explosion, no sudden silence. Instead, it was like whispers fading from a crowded room. You notice the party is still lively, the music still playing, but some voices are gone, lost into the distance. The universe carried on with photons, electrons and baryons, but the neutrinos had already departed into the dark, free to travel almost without obstruction for the next 14 billion years. This cosmic background of neutrinos is still with us today, though it is even harder to detect than the faint microwave glow of the cosmic microwave background. The neutrinos are colder now, their energy is diluted by expansion, drifting at just a few degrees above absolute zero. Yet they are everywhere, a quiet ocean of ghostly particles that permeates every corner of space. In principle, each cubic centimetre of the universe holds hundreds of these relic neutrinos, a mist of ancient travellers who have not interacted with the rest of the cosmos since their departure. We have not yet directly observed the cosmic neutrino background. It is too faint, too elusive for our current instruments. But its existence is written indirectly into the mathematics of the Big Bang. Without neutrinos, the pattern of light in the cosmic microwave background would look different. The way ripples spread in water depends on every pebble that has been thrown. By studying those ripples, cosmologists can infer the presence of neutrinos, their masses, their subtle fingerprints left on the expansion of the universe. In this way, even the guests who left the party left footprints on the floor. Neutrinos remind us that not all participants in the cosmic story are loud. Some are quiet, understated, almost invisible, yet decisive. Without their early decoupling, the expansion of the universe would have taken a different pace, the balance of particles altered, the subsequent formation of matter affected. Their whisper shaped the song. Even if they never raise their voices, our understanding of neutrinos has grown slowly. In 1956, Clyde Cowan and Frederick Reines detected them for the first time using a nuclear reactor as their source. Their experiment was delicate, relying on a handful of rare interactions to reveal the existence of particles that were otherwise invisible. Since then, vast detectors have been built to capture neutrinos from the cosmos. The IceCube Observatory in Antarctica buries sensors deep in the ice to look for the rare flashes of light that occur when a neutrino finally collides with an atom. Other detectors fill giant underground tanks with water or liquid scintillators, waiting patiently for a ghost to brush against reality. These experiments remind us how faint neutrinos truly are. Imagine standing in a rainstorm, yet only a single drop of water touches you in an entire day. That is what it is like to wait for a neutrino interaction. Billions stream through you every second, yet only a vanishingly small number ever collide. And yet, by watching carefully, by listening patiently, scientists have learned to hear these rare drops, and, through them, to learn about the deep cosmos. Tonight, as you rest, picture the quiet departure of the neutrinos. The universe is still young, still less than a second old. The party is crowded, but some guests slip away through the door into the night. They do not return. They continue outward, endlessly, like messengers carrying news of the first second across billions of years. Even now they drift past you in silence, undisturbed, unnoticed. They are survivors of a moment so early that time itself was still finding its rhythm. The story of neutrinos is not just about what they left behind, but about what they promise. They hint at physics we do not yet understand, why they have such tiny masses, why they oscillate between different types, and whether heavier cousins once existed to tilt the scales in favour of matter. They are puzzle pieces, clues to mysteries still unsolved. But they are also poetry, whispers from the first second, gliding eternally through space, untroubled by stars, planets or galaxies. So as you close your eyes, you might imagine yourself floating in that ocean of ancient neutrinos, each one a faint relic of the universe's first heartbeat. They pass through you as you breathe, as you dream, as you rest. You cannot feel them, but they are there, as constant as the night itself. The neutrinos left the party long ago, yet their presence remains, quiet witnesses to the birth of everything. When you think of chemistry, perhaps you picture glass beakers in a laboratory, liquids bubbling on a stove, or the aroma of bread rising in the oven. Chemistry feels like something that belongs to Earth, to kitchens and classrooms. But the very first chemistry in the universe happened long before planets or people, when the cosmos itself was only a few minutes old. After the violent quark-gluon storm, after the delicate balance between protons and neutrons was set, the universe cooled just enough to allow these building blocks to join forces. This was the era of Big Bang nucleosynthesis, a time when the first elements were cooked into being in what might be called the cosmic kitchen. The menu was limited. Temperatures had dropped to about 1 billion degrees, still hot beyond imagining, yet cool enough that protons and neutrons could begin to stick together rather than be torn apart. Imagine a pot simmering on a stove. At first the heat is so intense that no ingredient can hold its shape. Everything boils furiously. Lower the heat just a little, and suddenly ingredients can bind, forming broths, stews, flavours. The early universe went through just such a transition. The roaring plasma calmed enough for particles to form the first nuclei, fragile recipes that would determine the flavour of everything to come. Hydrogen was the simplest and the most abundant. A lone proton, sometimes accompanied by a neutron, became the staple ingredient of the cosmos. Its simplicity was its strength. Stable, light and plentiful, hydrogen made up about 3/4 of all the matter. It was the flour in the universe's bread, the basic grain that everything else depended upon. Helium came next. 2 protons and 2 neutrons bound together into a nucleus that was remarkably stable. Helium accounted for about 1/4 of the mass of ordinary matter, glowing softly in the recipe of the stars. Think of it as the butter to hydrogen's flour, a complementary ingredient that gives texture and richness. Without helium, stars would not burn as they do, nor shine with the same steady light. A trace of lithium was formed as well, though only in the faintest amounts. Lithium was the spice in the recipe, a pinch that did not dominate the dish but added nuance. Later, in the hearts of stars, heavier elements would be forged, carbon, oxygen, iron. But in this first cosmic cooking, only hydrogen, helium, and a hint of lithium were on the menu. The proportions were delicate, determined by the balance of protons and neutrons set just moments earlier. Had there been more neutrons, the universe might have been weighed down with heavier nuclei, unstable and prone to decay. Had there been fewer, helium would have been scarce, and the chemistry of stars would have unfolded very differently. Instead, the ratio was just right, allowing about 75% hydrogen, 25% helium, and a trace of lithium to emerge. This simple recipe became the foundation of everything. Stars that would burn hydrogen into helium, galaxies built of those stars, and eventually the carbon-based life that ponders the story today. In a sense, the universe was like a cook, who had only a few ingredients, but infinite patience. The first attempt produced a very limited dish, but one with the perfect proportions to support later creativity. Hydrogen was abundant fuel, helium provided stability, and lithium added a small touch of variety. With these alone, the universe could not yet produce life or complexity. But they were the foundation stones, the first steps on the long path toward richness. To bring it closer to daily life, picture making bread with nothing more than flour, water, and yeast. It is simple, perhaps even plain, but it is nourishing. Over time you can add spices, oils, seeds, and sugars, creating endless variations. The early universe did something similar. Its first bread was plain, hydrogen and helium, but it was enough to feed the stars, enough to give them fuel to burn, enough to let them, in time, bake heavier elements in their cores. Without that plain bread, the later feast would have been impossible. Big Bang nucleosynthesis lasted only about 20 minutes. In that brief time, nearly all of the helium in the universe was created. Afterward, the cosmos cooled too much for nuclear fusion to continue on its own. The oven door closed, so to speak, and the recipe was set. The universe carried this simple chemical inventory for hundreds of millions of years, until the first stars were born. Those stars, acting as new ovens, would reignite the process, forging carbon, oxygen, nitrogen, and iron. But the basic pantry, hydrogen and helium, was stocked in those first few minutes and has never changed since. Even today, we can measure the abundance of these elements and find them to be exactly what Big Bang nucleosynthesis predicts. It is one of the strongest confirmations of the Big Bang model. The fact that the stars are mostly hydrogen and helium, the fact that we can see helium lines in the light of distant galaxies, the fact that lithium appears only in small traces, all of this is written into the fabric of the cosmos, an echo of that first recipe. As you sit in your room tonight, perhaps with a warm drink or a blanket, consider that the hydrogen in the water before you, the helium in a balloon floating at a birthday party, even the faint lithium in a smartphone battery, all are descendants of that first chemistry. They are relics of a cosmic kitchen that operated for only a few minutes nearly 14 billion years ago. The most ordinary objects around you, the most trivial atoms in your body, are ancient beyond measure, born in the first simmering of the universe itself. And so the universe, in its first chemistry, was humble but decisive. It didn't craft gold or silver. It did not forge complex molecules. It didn't create DNA or flowers. It made hydrogen, helium, and a trace of lithium. Simple, plain, unadorned. Yet from those ingredients came everything else. Sometimes the simplest recipes are the most powerful. Sometimes 3 ingredients are enough to cook a cosmos. When you light a candle in a dark room, photons pour outward almost instantly, racing to the walls, bouncing off the furniture, reaching your eyes in a fraction of a second. We are so used to light being swift and free that it is easy to forget that in the early universe, light was not free at all. For hundreds of thousands of years after the Big Bang, photons could not travel any meaningful distance without being scattered, absorbed, or deflected. The cosmos was filled with charged particles, protons, electrons, and their companions, and every photon that tried to move forward collided with them almost immediately. It was a time when the universe glowed brilliantly, but hid its glow from itself, an age we call the opaque era. The density of the young cosmos was extraordinary. Imagine standing in a fog so thick you cannot see your own hand. The droplets of water scatter the light, sending it in every direction, robbing it of clarity. In the early universe, the fog was not made of water but of free electrons, floating without partners, constantly jostling with photons. Each collision deflected the light in a new direction, and the photon's journey was cut short, only to begin again in another random path. Instead of straight lines, photons traced drunken zigzags, trapped in a maze of charged particles. This state is described by physicists as a plasma, a sea of ionized matter where nuclei and electrons are not yet bound together into neutral atoms. Plasma is common in the universe. The sun's surface is plasma, fluorescent lamps glow with it, lightning briefly creates it in the atmosphere, but the early universe was plasma everywhere. A vast, all-encompassing fog that filled every corner of space. To imagine what it looked like is tricky, because no eye could have seen it. But if you could, it would not be blackness. It would be a blinding, uniform glow, as though you were inside the hottest fire, yet unable to see beyond the nearest flicker. And because light could not escape, the universe carried no visible image of its own infancy. unlike the cosmic microwave background that comes later, which we can now map with satellites. The opaque era left no photograph, no direct view. It is as though the curtains were drawn across the cosmic stage, and behind them the actors prepared in silence, waiting for the moment when the curtains would finally be pulled back. The trapping of light also meant that the universe's energy was evenly spread. Every region was bathed in the same scattering, the same bouncing of photons, so temperature differences could not persist. Imagine stirring cream into coffee. At first, streaks of white and brown remain, but as you stir, the mixture becomes uniform, every sip the same. In the same way, photons scattering endlessly through the plasma smoothed out variations, ensuring that when light finally escaped, it would reveal a remarkably uniform universe. The sheer time scale of this opacity is humbling. For 380,000 years, light was caught in this fog. To us, that number sounds immense, longer than recorded history, longer than the span of civilizations. But in cosmic time, it was the blink of an eye. The universe today is nearly 14 billion years old. The opaque era was less than a single breath in comparison, and yet it was decisive. During those years, matter and radiation remained coupled tightly, shaping the patterns that would later emerge in the microwave background and in the structures of galaxies themselves. The analogy of fog is useful, but it is not entirely complete. Fog on Earth is temporary. Sunlight eventually burns it away. The early universe's fog was lifted not by external warmth, but by cooling. As the cosmos expanded, its temperature dropped. Protons and electrons, which had resisted union in the furnace, finally slowed enough to combine into neutral hydrogen atoms. Once they joined, they no longer scattered photons so effectively. The fog began to thin, though the true clearing would come later, during the epoch of recombination. For now, we remain in the opaque age, when every photon was trapped in a restless crowd. If you want to imagine what it felt like, think of being in a room with too many mirrors. Every ray of light you shine bounces instantly, never reaching a clear path. Or imagine trying to walk through a forest so dense with trees that each step is blocked, forcing you to turn and twist in endless detours. The photon's life was just such a forest. Constant deflection, constant redirection, never freedom. Only when atoms formed did the forest thin enough for straight paths to open. Yet this entrapment was not wasted. It helped the universe reach its astonishing uniformity. Without those billions of years of scattering, the cosmos might have been patchy, irregular, inhospitable. The constant collisions were like a lullaby sung too often, smoothing every variation into a steady rhythm. The trapped light kept the universe even, balanced, prepared for the moment when the curtains would finally part. Even today, the remnants of that trapped light linger. Though photons from that era could not escape directly, their influence is written in the distribution of matter, in the faint acoustic waves that rippled through the plasma like sound through a drum. Astronomers can still trace those waves in the large-scale clustering of galaxies, subtle patterns that echo the music of the opaque era. The photons could not leave us pictures, but they left us rhythms, and the universe still hums with their memory. Tonight, as you close your eyes, imagine yourself inside that fog. Not a fog of water, not a fog that chills your skin, but a fog of light itself, dazzling yet unseen, photons bouncing endlessly, every path blocked. It is not frightening but strangely calming, like being wrapped in a thick blanket of glow. In that glow, the seeds of galaxies and stars were still hidden, waiting. The fog was not the end but a prelude, a soft veil that would one day lift to reveal the first true sight of the cosmos. There is a moment in every morning when the world shifts from shadow to light. The air may still be cool, the birds may still be quiet, but the first rays slip past the horizon, and suddenly everything is visible. The universe experienced such a dawn, not after a night of hours, but after hundreds of thousands of years. For so long, light had been trapped, bouncing endlessly through the fog of plasma, never travelling freely. Then, about 380,000 years after the Big Bang, the fog lifted. Electrons finally joined with protons, neutral atoms formed, and photons, those restless travellers, were released to journey without hindrance. This was the epoch of recombination, and the light that escaped then is still with us today, stretched into the faint glow of the cosmic microwave background. To imagine this transition, return to the picture of a thick fog. You cannot see far. Every beam of a flashlight is scattered. Every step is uncertain. Then the fog thins, sunlight streams in, and for the first time you can see the landscape beyond. The early universe cleared in much the same way. Until recombination, free electrons scattered every photon, keeping the cosmos opaque. When electrons paired with protons to form neutral hydrogen, the scattering ceased. Suddenly the road was open, and light could travel in straight lines. The universe became transparent, and it has remained so ever since. This moment was not just about visibility, it was about memory. The photons that streamed out at recombination have been travelling ever since, stretched by the expansion of space into microwaves, faint in frequency but still detectable. They carry with them a picture of the universe as it was in its infancy. When satellites like COBE.map and Planck have mapped this background radiation, they have given us a snapshot not of galaxies or stars, but of the universe itself as a newborn. The patterns in that light, tiny temperature differences, 1 part in 100,000, are the fingerprints of the ripples seeded during inflation. Ripples that would later grow into galaxies and clusters. Think of it as opening curtains after a long foggy dawn. Behind them is not a full-grown forest, but the bare soil, already ridged and furrowed, where the trees will one day stand. The cosmic microwave background is not the forest itself, but the first glimpse of the soil patterns that determined how the forest would grow. By studying those faint imprints, cosmologists learn about the seeds of cosmic structure, the density of matter, the speed of expansion, even the geometry of the universe. The sheer evenness of the background is striking. It is almost the same in every direction, as if the whole sky were painted in one uniform shade of pale light. Yet the tiny variations are even more important. They are the whisper of structure, the small irregularities that gravity would later amplify. Without them, the universe might have remained smooth forever, with no galaxies, no stars, no planets. The faint blotches in the microwave background are the ancestors of every cosmic structure. The MAP and Planck, 2 great space missions, gave us the clearest pictures of this light. WMAP, launched in 2001, produced detailed maps showing the mottled texture of the sky at microwave frequencies. Planck, launched by the European Space Agency in 2009, refined the picture even further with exquisite precision. These missions revealed not only the pattern of fluctuations, but also the age, composition, and fate of the universe. By looking at the oldest light, we learned that the cosmos is about 13.8 billion years old, that it is mostly dark matter and dark energy, and that its geometry is nearly flat. The background light is more than a glow. It is a cosmic ledger, recording the essential properties of reality. If you wish for a softer analogy, think of an old photograph tucked into a family album. The picture is faded, the colours muted, yet the outlines of faces are still clear. You may not see every detail, but you glimpse the beginning, the ancestry of what later became. The cosmic microwave background is such a photograph. Blurred, faint, stretched into microwaves, but still carrying the outlines of the infant cosmos. When we gaze at it through our instruments, we are looking directly into the cradle of everything. It is humbling to realise that this light has been travelling for nearly 14 billion years, passing through expanding space, cooling, stretching. Each photon has been on a journey longer than any human mind can truly imagine. And yet when it arrives in the dish of a radio telescope or the sensors of a satellite, it is as if it has been carrying a secret across eternity and finally shares it. The whisper is faint, but unmistakable. This is what the universe looked like at its first dawn. Tonight, as you listen in the quiet, you might imagine the curtains being pulled back on that foggy stage. The light does not burst forth like fireworks. It glows gently, uniformly, like the first hint of morning. The photons slip past the newly formed atoms, free at last, filling space with a glow that will never fade. You're surrounded by that glow even now, though your eyes cannot see it. Every patch of sky, no matter where you look, carries the faint microwave hum. It is a lullaby older than any song, a background note in the symphony of the cosmos. And so, the first light broke free. The universe was no longer opaque, no longer hidden behind a veil of plasma. It became visible to itself, carrying forward the imprints of its earliest ripples. That light has never stopped travelling, never stopped whispering its story. It shines still, faint but faithful, the oldest photograph we possess, a reminder that the fog will lift, the dawn will come, and the universe, like every morning, will reveal its face. When you pour milk into coffee, swirls appear, tiny streaks of white curling into brown, twisting and folding until they form patterns. At first the swirls seem delicate, almost random, but with time they spread, mingle and settle into larger structures. The early universe behaved in a strangely similar way. Inflation had stretched out the tiniest quantum ripples, turning them into slight variations in density across space. They were not dramatic, just faint wrinkles in the fabric of the newborn cosmos. But gravity is patient, and over millions of years it would pull on those wrinkles, tugging matter toward the denser spots and away from the emptier ones. In this way, the ripples became patterns, the first outlines of galaxies and clusters of stars. At the moment when the cosmic microwave background was released, these ripples were visible as tiny temperature differences, hotter regions where matter was slightly thinner, cooler regions where matter was slightly denser. The difference was minuscule, only about 1 part in 100,000. If you held a cup of tea and noticed one side was a fraction of a degree warmer than the other, you would hardly consider it remarkable. Yet those faint differences were enough for gravity to begin its slow work. Over time, the denser regions grew denser still, attracting more matter, while the thinner regions became emptier, releasing their contents. The universe was beginning to sort, itself guided by gravity's invisible hand. Think of foam on a cup of cappuccino. At first it is a froth of bubbles, random and chaotic. But as the foam settles, larger bubbles rise, smaller ones merge, and soon a pattern appears, ridges and swirls, an order within the froth. The universe's early density fluctuations worked in much the same way. They were the foam of creation, chaotic yet structured, from which galaxies would eventually take form. The process was slow. Gravity moves on patient timescales, accumulating matter grain by grain, like sand falling into a dune. For hundreds of millions of years after a combination, the universe was dark, filled with neutral hydrogen gas, but no stars to light it. This is sometimes called the cosmic dark ages. Yet even in this darkness, gravity was weaving its patterns. Invisible filaments of matter grew denser, knots thickened, and the first hints of structure emerged in the silence. Dark matter played a central role in this process. Unlike ordinary matter, dark matter does not interact with light, but it does feel gravity. It gathered more quickly, forming a kind of skeleton beneath the visible universe. Ordinary matter followed, drawn into the wells of gravity carved by dark matter. Without dark matter, The ripples might never have grown strong enough to form galaxies in the short time available. It is as though the universe had an invisible scaffolding, a framework upon which the visible structures could be built. You might picture it like dough sprinkled with raisins. If the dough is uneven, some spots with more raisins than others, then as the dough rises, those clumps grow more obvious. Gravity worked in the same way, amplifying the unevenness until clumps of matter grew into galaxies, and filaments of matter stretched between them. What began as the faintest irregularities in the afterglow of the cosmic microwave background became the architecture of the universe. It is humbling to think that everything we see, the Milky Way above us, the spiral arms of Andromeda, the vast clusters like Virgo or Coma, trace their origin to fluctuations so small they seemed almost negligible. If you had looked at the universe 380,000 years after the Big Bang, you might have said it was uniform, empty of promise. Yet within that smoothness were seeds, like tiny ripples in sand that foretold the dunes. Those seeds required only time, patience, and gravity to bloom into galaxies. Astronomers today can still see the imprint of those ripples, both in the microwave background and in the distribution of galaxies. The patterns match beautifully. The scale of fluctuations in the early light corresponds to the scale of clustering we observe billions of years later. It is one of the most satisfying confirmations of cosmology that the faint blotches in the sky's earliest light map directly onto the grand spirals, clusters and voids of today. If you want a gentler metaphor, think of music. At the beginning of a symphony. The notes may be quiet, almost hesitant, small motifs barely noticeable. But as the music develops, those motifs grow, are repeated, transformed, and eventually they dominate the grand climax. The early ripples were those motifs, whispers of structure that gravity amplified into the great chorus of galaxies. Tonight, as you rest, you might picture those first ripples not as numbers on a graph, but as faint undulations on a vast ocean. Imagine floating there, feeling the smallest rise and fall beneath you. They are almost imperceptible, but they are enough. With time, the swells grow, the waves mount, and an entire seascape emerges. That is how the universe grew its pattern, softly, invisibly, patiently, until the night sky became a tapestry of stars. When we look at the universe today, with telescopes that stretch their gaze across billions of light years, we find that the galaxies are not scattered at random. They form a structure vast and intricate, stretching far beyond anything we can truly picture in the mind's eye. Astronomers call it the cosmic web, a network of filaments and knots, voids and clusters woven together across the darkness of space. It is in many ways the largest pattern ever discovered, the grand design written into the fabric of the cosmos. To imagine it, think of lace held up to the light. The threads connect in delicate loops and intersections, while between them lie open gaps of emptiness. Or picture the strands of a spider's web glistening with dew at dawn, each filament connecting to another, forming a geometry both fragile and enduring. On the scale of hundreds of millions of light years, the universe looks like this. Galaxies string together in filaments, clusters gather at the intersections, and between them lie vast voids, empty spaces so enormous they dwarf even the largest clusters of galaxies. These patterns began with the ripples we spoke of before, tiny fluctuations stretched by inflation, amplified by gravity. Over time, the denser regions pulled matter toward them, forming long filaments, while the emptier regions lost matter and became great voids. Dark matter, though invisible, was the scaffolding. It formed the first filaments, its gravity tugging ordinary matter to follow. The result was a universe that looks less like a uniform sea and more like a woven fabric, with strands of galaxies forming a web across unimaginable distances. One of the striking things about the cosmic web is its beauty. Computer simulations, fed with the laws of physics and the initial ripples seen in the cosmic microwave background, produce images of this web that resemble living tissue, like the neurons of a brain connected by axons, or like rivers branching across a landscape. The resemblance is almost uncanny, as though nature repeats its patterns across scales. The same kind of branching that shapes the veins in a leaf also shapes the structure of the cosmos. Of course, the forces are different, the scales unimaginably far apart, but the patterns echo one another. The universe seems to favour connection, weaving filaments instead of scattering dust. In the middle of the filaments lie knots, clusters of galaxies where gravity has drawn the matter most tightly. These are like the intersections in a road map where many paths meet. The Virgo cluster, the Coma cluster, and countless others are such knots, homes to thousands of galaxies bound together. They shine with light from trillions of stars, yet around them stretch the quiet voids, darker than any desert night, places where galaxies are rare and loneliness reigns. Astronomers mapping this structure have found that the web is not random, but has a kind of rhythm. Filaments stretch for hundreds of millions of light years before giving way to voids, and then filaments rise again. The scale of these patterns reflects the physics of the early universe, the acoustic ripples that move through the primordial plasma before recombination. In a sense, the web is frozen music, the shape of sound waves imprinted on matter itself, now spanning the heavens. You might think of the cosmic web as a tapestry, but not one woven by human hands. It is a tapestry created by gravity, by time, by the interplay of matter seen and unseen. Each galaxy is like a bead sewn onto a thread, each cluster a knot where threads cross, and the whole stretches endlessly, a design far larger than any loom could hold. To gaze at it, even in imagination, is to feel the scale of existence pressing gently at the edges of your thoughts. The voids are just as important as the filaments. In their emptiness lies contrast, and contrast creates structure. Imagine reading a book with no spaces between the words. The text would blur, impossible to decipher. It is the gaps, the silences that give meaning to the words. In the same way, the cosmic voids give form to the filaments, highlighting their strands, making the web legible. Without emptiness, there could be no pattern. Even now, galaxies continue to move along the filaments, drawn slowly toward clusters, sliding down the threads like beads pulled toward a knot. The motion is so gradual it takes billions of years, yet on cosmic timescales it is relentless. We ourselves, with our Milky Way galaxy, are part of this flow, sliding gently along the Laniakea supercluster, drifting toward the great attractor, bound within the threads of the cosmic web. For astronomers, mapping this structure has been one of the triumphs of modern science. Surveys like the Sloan Digital Sky Survey have plotted millions of galaxies, turning the night sky into a three-dimensional chart of filaments and voids. Computer models, seeded with inflationary ripples, reproduce the same patterns with eerie accuracy, confirming that our understanding of the universe's growth is on the right path. When simulation and observation overlap, it is like hearing a piece of music played by two different instruments and recognizing the same melody. Yet beyond the science, the image of the cosmic web carries a quiet poetry. It reminds us that the universe is not chaos but connection, not randomness but rhythm. Across distances so vast that even light takes hundreds of millions of years to cross them, matter has woven itself into strands, knots, and emptiness. And here, in a small galaxy on one of those threads, life has emerged to notice the pattern, to trace the lace of existence, to whisper about webs in the dark. Tonight, as you lie back, you might picture the sky not as a scatter of stars, but as part of this vast network. Imagine the galaxies connected by threads of light, stretching beyond sight, weaving a web so large that the Earth itself is a grain of dust caught within it. There is comfort in that vision, for it tells us we belong to something immense yet ordered, something woven with care by gravity's hand. The ripples became patterns, the patterns became filaments, and the filaments became the web, and we, like every star and planet, are strands in that cosmic lace. Once the ripples had become patterns, and the patterns had woven themselves into filaments of the cosmic web, the stage was set for the next act, the birth of stars and galaxies. For hundreds of millions of years after recombination, the universe remained dark. Hydrogen and helium atoms filled space, but they were cool and invisible, absorbing and scattering light rather than producing it. This period, often called the Cosmic Dark Ages, was not silent in a physical sense. The universe still pulsed with energy, with matter drifting and gathering under gravity, but it was without stars, without the visible brilliance we now associate with the night sky. Gradually, the denser knots of gas along the filaments collapsed under their own gravity. Clouds of hydrogen and helium grew thicker, pressing inward until their centres heated to tens of millions of degrees. At that threshold, nuclear fusion began, and the first stars ignited. Their light pierced the cosmic darkness, transforming the universe from a place of quiet obscurity into one alive with illumination. The epoch of ionization had begun as the radiation from newborn stars ionized the surrounding hydrogen gas, turning the cosmos transparent again. These first stars were not like the ones we see today. They were giants, hundreds of times more massive than the Sun, burning furiously and living only for a few million years before exploding as supernovae. Their brilliance seeded the universe with heavier elements, carbon, oxygen, iron, elements that would one day form planets, oceans and bodies like yours and mine. Without those colossal first stars, the cosmos would have remained a simple mixture of hydrogen and helium. Complexity and ultimately life depended on their short but spectacular lives. As stars gathered into groups, the first galaxies formed. Small at first, irregular and fragile, they merged over time into larger spirals and ellipticals. Gravity is not tidy. It pulls galaxies together, lets them collide, merge and reshape. What we now see as the elegant pinwheels of spiral galaxies are the result of billions of years of this rough dance. Every galaxy carries scars of its history, collisions written into its shape, yet all are descendants of those first faint clumps of matter that collapsed after the Dark Ages. For decades, astronomers dreamed of seeing back to this epoch, to witness the first galaxies as they formed. Telescopes on Earth, and even in orbit like Hubble, revealed galaxies billions of light years away, but the earliest moments remained out of reach. The light of those galaxies had been stretched by expansion into the infrared, beyond Hubble's sensitivity. We knew the galaxies must be there, but they were hidden like faint embers smouldering behind smoke. Then came the James Webb Space Telescope, JWST, launched in 2021 with its golden mirror unfolded like a flower in space and its instruments tuned precisely to the infrared. Almost immediately, JWST began to glimpse galaxies farther and earlier than we had ever seen before. Some appeared less than 300 million years after the Big Bang, already surprisingly large and structured. Their existence startled astronomers who had expected the earliest galaxies to be small, tentative, just beginning to gather. Instead, JWST showed us cosmic toddlers who had grown as tall as teenagers, galaxies that seemed too mature for their age. This discovery did not disprove the Big Bang, as some early headlines breathlessly claimed. The evidence for the Big Bang is overwhelming, stitched into the microwave background and the abundances of elements. What JWST's glimpses did was remind us that our models of galaxy formation are still incomplete. Galaxies may form faster than we thought, or dark matter may clump differently than our simulations predict, or perhaps star formation in the early universe was more efficient than imagined. The puzzle is exciting, not alarming, for it shows that the universe still holds surprises, still resists being fully pinned down. To bring this into a gentler frame, imagine children who grow faster than expected. A 6-year-old who suddenly seems tall enough for 10, already reading books meant for older students, already showing signs of maturity that make you pause. The child is real. The growth is undeniable. What it tells you is not that your understanding of childhood was wrong, but that growth can happen in more varied and surprising ways than you assumed. JWST has shown us such children among galaxies, early ones that stretched taller and shone brighter than our models had prepared us for. There is also a quiet poetry in these glimpses. When you look at a photograph of yourself as an infant, you see both the strangeness of a face not yet formed and the unmistakable continuity of features that remain. In JWST's images, we see galaxies that are unfamiliar in their youth but already carry the outlines of the vast spirals and clusters we know today. They are family portraits of the cosmos, showing us our galactic ancestors at an age when everything was just beginning. The cosmic web guided their formation, filaments drawing gas into streams that fed the growing galaxies. Dark matter halos provided the gravitational wells, the invisible cradles in which gas could settle and stars could ignite. Over time, galaxies clustered along these filaments, forming the nodes we now see in large-scale maps. JWST has given us the first real photographs of that story in its earliest chapters, pages of a book we had only guessed at before. And so, the Dark Ages ended not with a bang but with a glow. Countless stars igniting, galaxies forming, and light finally filling the universe. The cosmos became not just transparent but luminous, patterned with filaments, dotted with galaxies, vibrant with energy. From then on, the story of the universe would be one of structures growing, merging and evolving, until eventually it produced stars like the Sun, planets like Earth, and beings capable of telling the tale. Tonight, as you rest, imagine the sky not as it is now, but as it was then. The first points of light breaking a darkness that had lasted for hundreds of millions of years. Picture those galaxies glowing faintly, fragile yet determined, like candles lit in a vast cathedral of night. JWST has let us glimpse those candles, and in them we see our own beginnings, the first sparks in a story still unfolding. Every melody rests on certain notes, every building on certain proportions, every recipe on certain measurements. Change them too much, and the song collapses into noise, the building into rubble, the dish into something inedible. The universe too rests on numbers, constants so familiar to physicists that they are written with single letters, yet so mysterious that no one knows why they hold the values they do. These numbers, set in the first instance of the cosmos, shape everything that followed. They are not many, but they are decisive, and without their delicate balance, galaxies, stars, planets, and life itself would not exist. The most famous of these is the speed of light, represented by the letter C. It is not just a number that tells us how fast beams of light move, it is a boundary woven into the structure of reality. Information, energy, and matter cannot travel faster. If light were slower or faster by any large factor, the unfolding of the cosmos would change completely. A slower light might have meant that stars and galaxies could not spread their warmth efficiently. A faster one might have altered the very interplay of time and space. The number feels arbitrary, about 300,000 kilometers per second, yet it sets the pace of everything. Then there is the gravitational constant, G, a measure of how strongly matter attracts matter. It seems small, almost timid, compared to other forces. You can lift a book with your hand, easily overpowering the pull of the entire Earth, yet over vast scales gravity dominates, gathering stars into galaxies and galaxies into clusters. If G were a little stronger, the universe might have collapsed back in on itself before stars could ignite. If it were weaker, galaxies might never have formed at all. Gravity's gentleness is precisely what gives the cosmos time to breathe, to build, to evolve. Among the most subtle of numbers is the fine structure constant, often written as alpha. whose approximate value is 1 over 137. This constant governs the strength of electromagnetism, the force that shapes atoms, molecules, and chemistry. Change A by even a few percent, and atoms would not hold together in the same way. Chemistry as we know it would vanish. Some have called 1 over 137 a magical number, a fingerprint of the universe's mystery. Why this fraction and not another? No one knows. But in its quiet balance, matter gains stability, electrons orbit nuclei, and the bonds of life become possible. Even the masses of particles, the proton, the neutron, the electron, are delicately tuned. A neutron is just slightly heavier than a proton, a difference small in percentage but enormous in consequence. Because of that difference, free neutrons decay while protons endure. Had the numbers been reversed, the universe might be filled with neutrons instead, unstable and short-lived. Atoms would never have formed. Likewise, if the electron were much heavier, atoms would collapse. If it were much lighter, molecules would fail to bind. Each value is a thread in the tapestry, fragile and irreplaceable. These constants are not decorations added later. They were there from the first second, stitched into the universe's fabric as it cooled and expanded. Physicists often speak of this as fine-tuning, not in the sense of deliberate adjustment, but in the recognition that small changes would have led to drastically different outcomes. It is as though the universe is an instrument, strung with delicate strings, tuned just so. Pluck them in harmony, and a cosmos of stars and life emerges. Detune them, and the music fades into silence. The metaphor of music is helpful. Picture a guitar tuned for a song. If one string is slightly off, the whole song feels wrong, even if the rhythm continues. The universe's strings, C, G, alpha, particle masses, are tuned together. The result is not a literal melody, but the harmony of stars burning stably, galaxies clustering, chemistry forming, and life evolving. Had the tuning been off, the music of existence might never have played. Some find this idea unsettling. Why should the numbers be what they are? Why 1 over 137 and not 1 over 140? Why such a gentle gravity? Why this speed of light? Theories like the multiverse suggest that perhaps countless universes exist, each with different numbers, and we find ourselves in this one because only here could life arise to ask the question. Others suggest that deeper laws still unknown may one day reveal why these values must be as they are. For now, we simply observe their precision and marvel at their consequences. Consider for a moment how close you are to these constants. The warmth of the sun on your skin depends on the strength of gravity and electromagnetism, balancing to allow fusion in its core. The air you breathe is made of molecules bound by the fine structure constant. The very act of sitting, feeling weight in your body, is gravity's patient pull, moderated by G. Every ordinary sensation is an echo of those cosmic numbers, as though the universe whispers them in every detail. When you tune a guitar or a piano, there is a quiet satisfaction in hearing the strings fall into harmony. The notes resonate, the chords settle into place, and suddenly the music flows. The universe feels like that. A song already tuned before anyone could listen. A harmony woven into the silence of the first second. You do not need to know the equations to feel the wonder. It is enough to know that without this tuning, nothing familiar would exist. Not the stars above you, not the ground beneath you, not the breath in your lungs. Tonight, as you drift towards sleep, imagine the cosmos as an instrument strung across time, each constant a string vibrating in balance. The song it plays is not loud but steady, a hum that has lasted for billions of years, a harmony in which galaxies, stars, and life are but verses. The numbers do not explain themselves, they simply are, and in their quiet being, they give rise to everything. Time is something we take for granted. The clock ticks forward, days turn to nights, seasons follow one another, and our lives seem to move in one direction only. Yet physics itself does not insist on such a direction. The fundamental equations describing particles and forces are, in most cases, perfectly happy to run forward or backward. A ball falling can just as easily be described as a ball rising, if you flip the signs in the equations. A collision between two particles looks the same whether you rewind the film or let it play. So why, in our everyday world, does time have an arrow? Why do we remember the past but not the future? Why does tea cool in a cup instead of heating spontaneously? Why do stacks of cards tumble but never restack themselves? The answer lies in entropy, a measure of disorder, or more precisely the number of ways a system can be arranged. A neat deck of cards has low entropy. A shuffled one has high entropy because there are many more ways to be messy than to be ordered. In our universe, entropy almost always increases. Things fall apart, spread out, mix, and scatter. This tendency is not a law written separately, but a statistical truth. There are simply more ways for things to be disordered than ordered, and so time flows toward disorder, and we feel its current as the arrow of time. But here lies a puzzle. If entropy always increases, then at some point in the past it must have been very low. Otherwise there would be no room for increase, no way for time to flow, and indeed, the early universe seems to have begun in a state of astonishingly low entropy. At the moment when matter and radiation filled space nearly uniformly, when fluctuations were tiny and evenly spread, the cosmos was far more ordered than it is today. That improbable order was the foundation for everything, for the growth of galaxies, for the unfolding of history, for the sense of time itself. To imagine this, think of a stack of cards placed neatly on a table. You know that if you bump the table, the stack will tumble, scattering across the floor. That is the natural direction, from order to disorder. What is strange is not that the cards fall, but that they were ever stacked so neatly in the first place. The early universe was like that neat stack, improbably tidy, perfectly balanced, waiting to tumble. Another way to picture it is with sand on a beach. Left alone, the grains scatter in the wind, spread across the shore and blend into chaos. But at the beginning, the universe's sand was somehow sculpted into a simple, delicate castle. The winds of time then eroded it, spreading the grains, increasing entropy, shaping the complexity we now see. The mystery is not why the castle fell, but how it was ever built so neatly to begin with. This low entropy beginning is one of the great unsolved questions of cosmology. Why was the early universe so ordered? Some suggest that inflation itself may have smoothed things out, creating a uniform state that set entropy low. Others wonder if deeper principles are at work, laws we do not yet know. For now, it remains an open mystery, one of those quiet questions that hum in the background of physics, unanswered but vital. Entropy is not only about the cosmos, it shapes every moment of your life. When you breathe in, the oxygen spreads through your blood, dispersing into cells, increasing disorder, but also fueling life. When you drop a piece of paper, it flutters down, spreading energy into the air. When you remember something, your brain stores patterns in a way that reflects the asymmetry of time's flow. Even your memories themselves are a consequence of entropy. You can remember the past because traces of it remain, but the future leaves no such marks. The arrow of time is not just physical, but emotional. We grow older, not younger. We carry experiences behind us, not ahead. We feel the flow of time as one of the deepest truths of existence, and yet at its root it comes from a statistical fact, from the tilt of the universe toward disorder. Entropy makes time a river, and we drift along its current, unable to paddle back upstream. Still, disorder is not simply loss. In the spreading, in the tumbling, in the mixing, beauty arises, Stars burn by dispersing ordered fuel into radiant light. Galaxies evolve as matter spreads and gathers again. Even life itself emerges from gradients, from the flow of energy from hot to cold, from the decrease of order in one place balanced by the rise of structure in another. Entropy gives us time, but it also gives us change, growth, story. Tonight, as you reflect in the quiet, you might picture time not as a relentless arrow, but as a deck of cards slowly tumbling. Each card falls into a new position, and though the stack grows messier, patterns appear. Perhaps a streak of red here, a cluster of black there. The tumble is inevitable, but it is not meaningless. Out of the fall emerges shape. Out of disorder comes variety, and out of entropy comes the very possibility of living in a universe with history. So the arrow of time points forward because the universe began in a state that was improbably neat, improbably low in entropy. That neatness did not last. It could not last. But in its unravelling, time was born, and we were given a direction to follow, a way to tell stories, a way to grow old, a way to dream of futures even if we cannot remember them. Entropy is the current, and we are leaves upon it, carried into the unknown. We have travelled a long road together tonight, from the faint edge of possibility before the universe's first moment, through the searing heat of the Planck era, across the great stretch of inflation, into the crack of symmetry breaking, the awakening of the Higgs, the dance of quarks, the fragile balance of protons and neutrons, the vanishing of antimatter, the quiet departure of neutrinos, the first chemistry of hydrogen and helium, the fog that trapped light, the dawn of the cosmic microwave background, the ripples that became patterns, the weaving of the cosmic web, the birth of galaxies and stars, and the delicate tuning of constants and entropy that shaped it all. The path we traced is a story stitched together by science, but also softened by wonder. What do we know? We know that the universe began in a hot, dense state nearly 14 billion years ago. We know that in its first second, unimaginable energies sculpted the fabric of space and time. We know that inflation stretched tiny quantum ripples into the seeds of galaxies. We know that forces split apart, particles gained mass, and matter won a narrow victory over antimatter. We know that neutrinos slipped away, silent witnesses to the dawn. We know that hydrogen and helium formed in the first minutes, that light was trapped for hundreds of thousands of years, and that when it finally broke free, it left us a glowing map still visible today. We know that galaxies grew from faint ripples, that stars ignited and died, that planets formed, and that eventually life arose to look back at it all. And what don't we know? We do not know what happened before the Planck time, when gravity and quantum mechanics collide into silence. We do not know why the universe began with such low entropy, or why the constants of nature are tuned just so. We do not know the full story of why matter triumphed over antimatter, or whether heavy neutrinos or other unknown processes tipped the scale. We do not know whether inflation was a one-time event or part of an eternal process, budding new universes beyond our sight. We do not know if our cosmos is one among many, a bubble in a foam of universes, or if it is all there is. Theories stretch outward into possibility. Cyclic universes, Penrose's conformal cycles, brain collisions in higher dimensions, eternal inflation leading to multiverses. Each is a story we can tell, grounded in mathematics, but each remains unconfirmed. These are not failures, but invitations, reminders that science thrives on mystery. What we know is vast compared to what we once knew, but what we don't know is vaster still, and perhaps that is exactly as it should be. There is beauty in this balance between knowledge and unknowing. To stand under the stars is to feel both secure and small, secure in the knowledge that physics can explain the light in the sky, small in the recognition that much lies beyond explanation. The universe began not with clarity but with possibility. It is as if reality itself whispered, "Here is a story, see how far you can follow it." We have followed it far, and still the trail extends into the mist. You might compare it to reading an ancient manuscript. Many pages are intact, written clearly in ink we can still decipher. But between the pages are gaps, missing lines, places where the parchment has burned away. We piece together the story from what survives, and we guess at what was lost. The tale remains incomplete, yet beautiful, perhaps more beautiful for its gaps. The universe's story is like that manuscript, a book with torn pages, a song with pauses we cannot fill, a painting with spaces where the brush never touched. And yet, here you are, listening. That fact alone is part of the mystery. From the tiniest imbalance in matter and antimatter, from the quiet departure of neutrinos, from the fine-tuning of constants, from the slow unfolding of entropy, life has emerged. Life capable of asking questions, of tracing the first second, of wondering what lies beyond the beginning. The atoms in your body were once quarks in the plasma, neutrons in helium, carbon in a star's heart. You're not separate from the story, you're its continuation. As you drift into rest, let the questions remain open. Do not hurry to close them, for the openness itself is a kind of peace. The universe may have begun with a bang, or with a stretch, or with something stranger still. It may be one of many, or the only one. Its constants may be tuned by deep necessity or by chance among infinities. We do not yet know, and perhaps we never will. But the not knowing is not emptiness. It is space, like the silence between notes in a lullaby. Space that allows the melody to breathe. So let us end softly. The first second of the universe is both known and unknown, both mapped and mysterious. We can trace its outlines. We can feel its echoes in the glow of the microwave background and the abundance of hydrogen. We can glimpse its consequences in galaxies and stars. But its core remains wrapped in mystery, a place where science and wonder meet. The universe began not with clarity, but with possibility. And possibility, perhaps, is the gentlest beginning of all.